Hello guys, welcome back. I hope you enjoyed your weekend. Today should be a really simple day. We're just going to review some of our algebra stuff that we talked about last Friday, our algebraic properties, and then we're going to use some algebraic proofs. We will have at least one problem on the test, which will be next Wednesday, so not this Wednesday, but the Wednesday after that. That has to do with some algebraic proofs, so make sure we know how to do it. But today should be pretty simple, just some kind of quick review. So let's start out with reviewing our identity properties. So the key word is the identity. So for the additive identity, we want to know what do we add to something in order for its identity to remain the same. So our additive identity, a times 0 is still a, right? For the multiplicative identity, what do we multiply something by in order for it to remain the same? Well, that would be 1. And for the exponential identity, what do we take something to the power of in order for it to remain the same, which would be 1 as well. Then the algebraic properties, kind of the stuff that we talked about on Friday. So the commutative property is when we're switching the order of two terms. So we have a plus b is the same thing as b plus a. So notice the only thing that's changing here is we're switching the order of a and b. And notice that we're switching it about the addition sign. So this would be the commutative property of addition. Now we do the same thing with multiplication if we wanted. So this would be the commutative property of multiplication, because notice we're switching the order of a and b about the multiplication sign. Be careful, because sometimes when you see the commutative property of multiplication, you'll see it without the multiplication symbols or a raised dot, and it's just implied that we're multiplying between the two. Another one is the associative property. Now this is when we're changing who we're associating with or like grouping. So instead of adding the first two together with these parentheses, now we're going to add the b and the c together first, then add a at the end. So we're just changing who we're grouping with or who we're associating. This would be the associative property of addition. We can do the same thing with multiplication. And notice here we have some implied multiplication because it's next to the parentheses here. So no big deal. And then, oh yeah, by the way, sometimes you might see this like that, because those would all be implied multiplication. Then we have the symmetric and the reflexive property. So the symmetric property just is we're switching the order just like commutative property, but now we're switching it about an equal sign. So notice how similar this is to the commutative property, except we're switching the order of a and b, and we're switching it about an equal sign. So it's kind of like the commutative property of equality, but no, it's just called the symmetric property. It has its own name. Then reflexive is very similar and often commonly confused with the symmetric property, and I see why. But instead of it being two different things that we're switching the order of, another example of that is oftentimes we'll say like 3 is equal to x, which is the same thing as x is equal to 3. So whenever we solve for an equation and we want x is equal to something, but we end up, with the x on the other side of the variable on the other side of the equal sign, it's okay because of the symmetric property, we can switch the order, right? So that's why the symmetric property is commonly used. The reflexive property, I don't know when this is ever used, but things are going to be equal to themselves. Actually, I do know when it's used. But we'll see it later in this year. Okay, so the reflexive is going to be like a is equal to a, of course, 3 is equal to 3, 7 is equal to 7, baby is equal to baby, and of course, here we have our gorgeous French bébé with some very angry eyebrows, some swag. Got the G chain going down, and the big watch, because that's how he rolls, and we're mirroring everything on the other side. Yeah. Sometimes I've even been known to give him horns. Those are not very good horns. And a trident, but I won't do that today. Okay, that's scary. I'll pretend like that never happened. Moving on, algebraic properties. Distributive, so whenever we have parentheses, we can distribute the multiplication through to the other two terms. So that would be 4b minus 4c. Transitive property is kind of fun. When we have a is equal to b, b is equal to c, it's kind of like dominoes. Allows us to skip over the b and go directly from a is equal to c. So no big deal. It's kind of fun. I can't fix that one. I'll do it later. Alright, so just a few other general definitions and terms that we need to know for geometry and specific that you'll be using in the proofs today, so make sure you know these are terms supplementary, adjacent angles, and linear pair. So do you remember what adjacent means? I know I'm asking you through the video, but adjacent means that they are two angles that are sharing a common side or a common ray. So right now these two angles are not adjacent because they're not touching, but as soon as I overlap them like that, now they're adjacent because they share this common ray, BD. Okay, so supplementary means that they add up to 180 degrees, so you can remember that because you can take the S, turn it into an 8, so it is supplementary. These two angles are supplementary because they form a straight line, And if they're adjacent as well, we call them a linear pair. So there's a special term when they're a linear pair. They were always going to be supplementary, right? They always added up to 180 because 65 plus 115 is 180. But when they were also adjacent, meaning they shared a common side and they were touching, that's when they formed a line when we added them together, okay? So that's the distinguishing between supplementary and a linear pair. A linear pair is a special supplementary set of supplementary angles that are also touching. So right now they're a linear pair, and right now they're just supplementary. Okay, then we have midpoints and segments. So this point here, B, I think, no I didn't, that's on the other one. Oh, spoilers. This point here is considered a midpoint when it cuts the segment into two congruent segments. So if we see here, we see C is congruent to C, or sorry, 6 is congruent to 6. Sorry, 6 is equal to 6, so their segments are congruent, so we can mark them with congruency marks, meaning B cuts segment AC in half. In other words, B is the midpoint of segment AC. So then we can write that AB is congruent to segment BC because their measurements are equal, and then B is the midpoint. Now a bisector is very similar to a midpoint, but a bisector is dealing with an angle. So bisector, an angle bisector, is going to cut an angle in half. So for instance, if we have this right angle here, which is perpendicular, and if BC, ray BC cuts it in half, then we're going to have 45 and 45. So just like a midpoint cuts a segment in half, a bisector is going to cut an angle in half. So if ray BC bisects angle DBA, so DBA, BC cuts DBA in half, that's true, then that means that the blue angle is going to be equal to the green angle, just like the blue segment is equal to the green segment. So anyway, that is what a midpoint and a bisector are and how we use them. Then we have a segment addition postulate. So if B is collinear to points A and C and it's in between A and C, then we know that points AB, or segment AB plus BC, is going to be equal to the whole thing, which is AC. So color coding it out, we have the blue plus the green is equal to the red. So visually, that's all that formula is telling you. Now what's nice is this works for any value of B. You're wondering, how does he do that magic? For any value of B that is in between A and C. So it doesn't matter how long AB and BC are, they're always going to add up to AC for any B that is strictly collinear and in between endpoints A and C. So kind of cool. Now the same thing happens with the angle addition postulate. So segment addition postulate, basically, if B is collinear, then AB plus BC is equal to AC. Angle addition postulate says if we have any ray that's in between the other two rays, then the blue angle plus the green angle is equal to the red angle. Just like here, blue segment plus the green segment is equal to the red segment. So we can add adjacent angles, so this means that if the two angles are touching or they share a common side, then we can add the angles together to get the bigger angle. The other thing is, from segment addition, we also get we can subtract segments as well. It's just by subtracting one of these to the other side. So AC minus the BC is going to be equal to AB. So if we know what the whole thing is, we know what the green part is, we can find the blue part by subtracting. Same thing happens with angle addition, by the way. We can subtract angles and we can add angles as long as they're adjacent. Okay, that was it. Wow, 8.5 minutes. That was super fast. So let's go through a few of the problems. I've also posted the solutions through all of these. The first 20, they've got an answer bank, but after that, you're kind of on your own. But you got the solutions, so you can always look them up if you get stuck. But it would have just been too much work for me to type out all the answer banks, and I don't think it would have been that helpful anyway on the proof. So I just want you to try them out on your own and see how you do. Alright, so name the property of equality or congruence that justifies going from the first statement to the second. So on the first one we have 3x is equal to y, and then now it's just x, so I wonder where the 3 went. Oh, there it is. Wow, talking to myself. I really miss being in class so that you guys could laugh at my jokes. But anyway, it looks like our 3 is now divided on both sides. So we divided both sides by 3. So this would be the division property of equality. So whatever I do to one side, if I divided one side by 3, I have to do the same thing on the other side as well. The 3's, they divided out to 1, simplify to 1, and then we were left with y over 3 on the other side. Now on this one we have the x and the y switching places. Alright, so we're switching places for the two variables x and y. They're separated by multiplication, so this would be the commutative property of multiplication. Number 21, So it says, given AB is the bisector of angle CAD, prove that x is equal to 9. So oftentimes when we do a proof, it's called a two-column proof. So we have our statements on the left and our justifications on the right, or our reasoning on the right. So the first time, they often restate whatever was given, so that's the information that we have, and notice there's a diagram that goes with it. So they say AB is a bisector of CAD. Well, that was told in the given part, so the first reasoning is just that it was given to us, so that's often what the first one is. And then after that, they tell us that angle CAB, so CAB is equal to angle BAD. Well, how do we know that these two angles are congruent? Well, if we go back, we know those angles are congruent because of the because it's a bisector, right? And bisectors cut angles in half. So if they tell us that BD is AB is a bisector, then that means, I guess I have to push that again. Anyway, that means that it cuts the angles in half. So this is from the definition of a bisector. So these might be a little bit tricky for you, but anyway, definition can be abbreviated DEF superscript N. I don't know why or where that came from, but I just picked it up from my teacher who taught me how to do proofs in college, Ms. Carver, so that's just how I've always written them, so that's probably how you always write them too. So definition of a bisector, or an angle bisector. Alright, next one we have here is they have the 7x plus 2 is equal to the 5 times x plus 4. Now, we got those values from the expression here by substituting in their expressions. Okay, so if we know that the angles are congruent, we know their expressions are equal, and we can set up an equation by plugging in those in. So this is just going to be simply substitution, so we substituted the expressions in for the measurements of the angles. Alright, then after that, it looks like we're doing a little distribution, so we're distributing the 5 through across the parentheses, and that's going to be just distribution property. And then from here, it looks like the 5x is being subtracted from both sides. So we subtract 5x to one side, we subtract it from the other side. That gave us the 2x and 0 on the other side. That's going to be subtraction property of equality. So if we subtract from one side, we have to do it from the other side to keep it balanced. Then on the next one, it looks like we're subtracting 2 from both sides. So again, subtraction property of equality. Then the last one, we're dividing both sides by 2, which is division property of equality. So you'll notice it's a lot of the same stuff over and over again. Just trying to make sure you guys remember this stuff. Okay, so that's the last one that I'm going to go over with you. Trying to keep the video short. Again, you guys can look at the solutions. Also, if you kind of watch the videos before 11 o'clock, you can join us for the live office hours as well. So it's been a lot of fun, and I can help you guys with that. But I'm trying to keep the videos short. And tomorrow we're going to start conditional statements, which is going to be our kind of the last kind of new topics that we're going to get into pretty heavy before we take that test. So anyway, that's it. I'll see you guys later. Have a good day.